All right. Thank you for the introduction, and thank you very much for the invitation. It's great to be here. It's a fantastic event, and it's wonderful to be back in Uruguay. So today I will be talking about privacy and security in machine learning. Those of you who were at Ian Goodfellow's talk on Tuesday may remember that he said that interpretability and security are the two hardest problems. Privacy is somewhere way up there as well. I'm not sure they're the hardest problems, but they're certainly different problems from many other problems in machine learning. They require different definitions, a different approach, sometimes a different way of thinking about techniques, a much more adversarial mindset because we have to worry about all the possible actions of attackers. And the standard machine learning evaluation techniques, which have been so successful over the last few years, are useful, but they're not sufficient for evaluating the privacy and the security of machine learning systems. At the same time, privacy and security are super important. They are essential, at least in the sense that if we don't manage to figure out how to build machine learning systems that have good security properties and that protect the privacy of information, that will really limit the usefulness of machine learning for many applications that we care about, where machine learning systems manipulate sensitive data or where they control access to important resources. So this is a very important domain. It's also a domain in which there has been quite a bit of activity in the last 5 years. And I'm not going to talk about all of that today. Of course, there wouldn't be time. But I would like to tell you about a few ideas and a few techniques and give you some sense of what's going on with references to a few papers from which you can begin to navigate the rest of the literature. So this is definitely very subjective and very partial, but I hope you will find it useful. Before we get into privacy and security, I'd like to take a step back and talk a little bit about how machine learning has evolved in the last few years. Once upon a time, the growth of machine learning and of AI more generally was basically the result of a happy coincidence. We had calculus for physics, we had probability theory also for other kinds of science. We had hardware, in particular GPUs, that were designed for graphics, but were very useful for doing neural nets. We had general purpose software, and building up the machine learning software was not too much work from that starting point. And we had data. And we built some data sets, and we were in business. But at least at first, machine learning did not have a very profound impact on hardware, software, or data. All of that has been changing, and changing a lot in the last few years. Increasingly, computing systems are being informed, they're being shaped by their applications in machine learning. For example, at a hardware level, hardware is getting designed with machine learning in mind. For example, some hardware is being built with reduced precision because sometimes reduced precision is sufficient for machine learning applications. Machine learning is also leading to new pieces of software. TensorFlow is one very rich, big system for machine learning. There's also other examples. Many intermediate representations in compilers for machine learning are new and motivated by machine learning specifically. Conversely, in the opposite direction, machine learning is starting to be applied in various parts of computing. For example, it's being used for optimizing in compilers. So you see there is flow in both directions, both machine learning influencing the design of computer systems and machine learning posing some new problems for computing. And we have the same thing going on in security and privacy. We have, on the one hand, ways in which machine learning is being applied to security and privacy. And it's been applied in many ways, both for offense and for defense. For defense, machine learning has often been used for detecting attacks. It can also be used in other ways, for example, for understanding access control lists or firewall rules and making sure that they're okay. They're also used for defense, for offense. For example, in the last couple of years, there have been some very nice papers on using neural networks for cracking passwords. I will not get too much into the details of this, but I can recommend to you an interesting report from last year, the malicious use of AI, forecasting, prevention, and mitigation. And you've seen this image in a few talks, so I thought I would put it up again. One of the points that this report makes, among many others, is that the fact that machine learning models are generating such realistic images can also be seen as a problem for security, or at least for trustworthiness. And there are many other problems that arise and that are covered there. Now, in the opposite direction, machine learning also gives rise to some new security and privacy problems at many levels. We have some very ordinary, very mundane problems that come up, for example, in systems like TensorFlow or PyTorch. They're large software systems, and they can have bugs and mistakes that can constitute vulnerabilities that can allow an attacker to break into a computer, for example, buffer overflows. So obviously, we need to deal with all of those. But there's also some new concerns, some new security concerns. Maybe I should give you a crash course in security. In security, we're fundamentally concerned with some very simple but very important kinds of properties. Secrecy, integrity, and often availability. Secrecy is about knowing where data goes, who gets to see the data. Integrity is essentially about guaranteeing the authenticity of data, guaranteeing it comes from the right place, essentially. Availability is making sure that one has access to data, or access to services, or access to other participants in the system. And that's particularly important for communication systems. In machine learning, we tend to focus on secrecy and integrity. Privacy can be seen as a particular flavor of secrecy. It's a flavor of secrecy where the data that we're concerned about is sensitive user data rather than the data of companies or governments or things of the sort. All right, so problems that machine learning poses appear in several places. Today we'll focus on supervised machine learning. It can also arise in unsupervised settings and possibly others, but the focus so far has been on supervised learning. And there we start with some training data from which we produce some learned parameters. And then at inference time, at test time, the machine learning model is presented with some test inputs, for example, an image, and then it has to produce some test outputs, for example, a label for the image. Each of these elements can be the target of attacks. The training data can be tampered with. It can be corrupted in malicious ways that lead the model to misbehave, to produce some very wrong predictions. This is called poisoning attack. The parameters may be derived in such a way that they contain bits of the training data, and they might allow an attacker to extract some of the training data. And this leads to a lot of privacy problems, and I will get a lot more into those in a few minutes. The test inputs can also be manipulated by attackers. In particular, there can be inputs that are designed to fool the models, and we'll talk more about those. And finally, the test outputs can be useful to an attacker that is trying to reverse engineer a model. And if the model is regarded as sensitive intellectual property, this kind of model theft can be a concern. And there has also been some work on that. Today, I'm just going to focus on two of these four kinds of problems. I'm going to talk a little bit about adversarial examples, and I'm going to talk a lot about the privacy of data, particularly the privacy of training data. So just a few slides on adversarial examples. Adversarial examples are inputs to machine learning models that are designed to confuse the models. They have been studied very widely in the last 5 or 10 years. These images are one of the most classic examples. On the left, there's an image of a panda classified as a panda with high confidence, 57%. And then one adds to it a pattern that looks like noise, but in fact, it's very carefully constructed by looking at gradients. And on the right is the resulting image, which the machine learning model says with super high confidence, 99%, that it's a gibbon. And this is very confusing. It's very disturbing because this is a mistake that humans would not make. And we're seeing machine learning systems achieving superhuman results in various applications. And then at the same time, they make these really silly mistakes. So that really poses questions on how much we can trust these systems. From a security perspective, it's also a concern. If, for example, we have a computer system that is supposed to be used only by gibbons, and someone puts in an image of a panda slightly modified and it passes for a gibbon, that's a kind of impersonation. More realistically, one could fool a system for recognizing users or a system for recognizing malware or something like that with adversarial examples. Now, as in this case, the perturbations to the adversarial examples have been the focus of a lot of the work in the literature, are very small perturbations. The two images look almost exactly the same. And this has led to the development of a lot of methods for protecting against adversarial examples, where one uses the normal training procedure but extends it a little bit with examples that are perturbations of normal examples, and this makes the models robust towards adversarial examples, and sometimes one can even prove formally that the models do not make mistakes, at least with some probability. One limitation of that work is that it only deals with very small perturbations, what are called epsilon ball perturbations. And not all perturbations that we might be worried about have that property. A couple of years ago, with some colleagues, I worked on bigger perturbations that in some settings might be realistic, and we're going to see an example of that. Here's a classifier that classifies this image as a banana. We tested by putting next to it a large image of a toaster. It's still a banana. But then when we put next to it a much smaller image with a lot of color, all of a sudden it's convinced it's a toaster. So what's going on? And the testing of the machine learning system that recognizes the banana with normal images of toasters is good for normal operation, but it's not sufficient to guarantee that an adversary who can put in a specially crafted image, even a small one, will not confuse the image recognition system. So stepping back, adversarial examples indicate bounds, indicate limitations on the accuracy of models in the presence of adversaries. Machine learning systems are used in the real world where there are adversaries, and we need to be careful in thinking hard about what an adversary can really do. Are adversaries limited to only very small perturbations? Are they able to put in bigger perturbations, for example, colorful images of little toasters, or what? And this is what in security we call a threat model. A threat model is a characterization of the possible actions of an adversary. And it's very useful to be explicit on what are the threats that we're trying to defend against, because otherwise we may be unpleasantly surprised. And this is an area of active research, and increasingly we're looking at how to define these threat models in a realistic way that allows us to protect machine learning systems. For example, machine learning systems that are supposed to detect malware, making sure that modified programs are not declared benign when in fact they contain viruses. In order to promote thinking about this space of adversarial examples where the modifications to images can be more than a few pixels, can be visible images, there is currently a contest, the Unrestricted Adversarial Example Challenge, which aims to encourage progress in making machine learning models robust to arbitrary modifications. And the challenge is about a very simple task of recognizing birds versus bicycles. But the recognition has to work even for modifications that change more than epsilon in the images, including rotations, but also many other possible modifications. All right, so that's all I wanted to say about adversarial examples for now. Let me go on to privacy. Privacy can arise in several places in machine learning systems. The main ones are the privacy concerns about training data that is used for constructing models. And then we may also be concerned about the privacy of the inputs to models after the models have been trained, the privacy at inference time. These two kinds of concerns, these two kinds of problems are a little bit different in several ways. For example, the training data we may want to keep around for days or weeks or even longer, while the data presented to the models can be quite ephemeral and therefore maybe less of a target for attacks. For that reason and others, I think the privacy of training data is the bigger, the more interesting problem, and that's the one I'm going to focus on. Some of this training data is, of course, very sensitive. Lorena talked about personal data in the context of education. Another set of examples arises in medicine. For example, there's been a lot of models for analyzing the illnesses in eyes, and we wouldn't want models to reveal physical information about patients or their diagnosis. So what can we do? For a start, we should do all the standard things that we know how to do. The first one, which is not emphasized often enough, is that data collection should be minimized. We shouldn't collect data unless we have a legitimate purpose for this collection that is going to be widely beneficial. We shouldn't be collecting data just because it may come in handy later on for some purpose unrelated to the immediate task. This is not a new idea, of course. However, it's even more important in the current world because we're collecting a lot more data because it's much more valuable for machine learning. So we have a bigger potential privacy problem to deal with. We should also do anonymization and pseudonymization, and Lorena already talked a little bit about that. Aggregation as well is important. Sanitization, like removing social security numbers. We should put access controls on the training data. And not only the training data, but also any data derived from the training data, unless we have a really strong reason to believe that the derived data is not sensitive. And finally, we should have policies for the retention or the deletion of training data, and we shouldn't keep the data around forever. We should throw it away from time to time if it is sensitive. So all of that's great, and we do all of that. The question is whether it's enough. Machine learning models are supposed to generalize, are supposed to apply to examples that were not used for training. And in that sense, they're not supposed to fixate too much on the details of the training data. So we might expect that they provide, by design, a kind of privacy guarantee. Moreover, many techniques for training with regularization encourage the models not to pay too much attention to the training data. For example, we may not optimize the models until the training loss is all the way down to 0. That's not the goal. However, generalization, although it might seem aligned with privacy, is only an average case property. And in privacy, we tend to worry about the worst case. We want to make sure that we can guarantee that we don't leak any sensitive information. Also, it's been shown that large models have enough effective capacity to fit even random training examples. Here I have a pointer to a paper that shows that one can take some of the standard large models and modify the training data, changing the labels to be random, and the models have enough capacity to learn this random labeling. So clearly, they're memorizing the labels. They're not generalizing from any pattern. They're simply recording what they have seen in the training data. And we actually see this in practice to some extent. this is an example from translation. And here we're translating from the Maori language, for which we don't have very much data, to English. And we input some complete garbage, dog, 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 dog. And what we get out is an apocalyptic prophecy, which it's not entirely clear why this happens, but it's a very sensible bet that some amount of biblical material was used in training the model, and that when the model doesn't know anything more to do, it just remembers this training data it had lying around and it outputs it. In this particular case, this is not a real privacy concern, of course, because the apocalyptic prophecies are in the public domain and they're not anyone's sensitive data. You think, so someone in the audience suggests it's an Easter egg. There are other examples which are along similar lines. I'm not sure. Internally, I have seen some even more examples of different natures. So it does look like models are memorizing stuff. And we need to be mindful of this and make sure that they don't regurgitate anything sensitive. So we want to make sure that someone who has a model cannot extract some of the training data. We also actually want a stronger property. We want to make sure that someone who has a model and an example cannot even tell if the example was used for training the model or not. These essentially want to prevent an attack that would be able to distinguish members from non-members for the training data set. And the motivation for this is that in some applications, even membership in a data set can be sensitive information. For example, imagine that you have some model that is about evaluating some treatment for some illness. Knowing that some patient's record is part of the data set already tells you that the patient probably has the illness, and that should itself be considered sensitive. Now, so we want to prevent these kinds of attacks, and we want to do it in a very strong world, in a very strong model, in which the attacker has complete access to the weights and the biases, all the parameters of the model. And this is a realistic threat model in the case in which the models are deployed on devices that the attackers may control, for example, models that are deployed on mobile phones. It's also a very convenient model for us, a very convenient way of thinking about the attack possibilities, because if we didn't do this, we would have to worry about how many times can the attacker access the model, and we would be doing calculations that bound the loss in privacy as a function of the number of requests that the attacker makes on the model. In this view of the world, the attacker has complete access to the model, and we're trying to provide guarantees even in that extreme case. We're going to define our objective, this preventing of membership attacks, in terms of differential privacy. And probably many of you know a little bit about differential privacy, have seen the definition. Would you please raise your hand if you have seen it? Okay, so I will review it, at least informally. So differential privacy is about preventing membership attacks, essentially. We have a training algorithm that is trained either on a data set with one set of users or a data set with all those users except for one. And the training algorithm produces two models, model 1 and model 2. And we want to talk about the possibility that an attacker, the person on the right, can distinguish these two models, can tell that one of the models was produced using the data from all the users, and the other model was used with data of all the users minus one. So let's call the data sets X and Y. The training algorithm is M. So the models are M of X and M of Y. And we would like to say that M of X and M of Y are equal, that we get exactly the same model with the two data sets. That's not going to be true, right? Because for one thing, the training is going to be stochastic. So even with the same data set, we're going to get different models different times. So we might say, well, they have the same distribution, but that's not going to be true because they come from different training sets. The best we can hope for is that they have similar distributions, m of x and m of y. And one way to say that they have similar distributions is to say that when the attacker applies a predicate to samples from the distribution, the two cases, the two possible worlds, give the same answer with high probability. So more precisely, for every predicate S, or for every set S, the probability that m of x is in S is very similar to the probability that m of y is in S. And here, ideally, we'd like them to be the same. Very similar actually means that they're within a multiplicative factor, e to the epsilon, and an additive factor, delta. Delta is going to be a small constant, which is seen as the probability of making a mistake, and it's typically about 1 over the size of the data set. Epsilon is supposed to be a small parameter. We would love for epsilon to be 0. In practice, it will typically be a single-digit number, somewhere between a half and 10 or something like that. Those are the values we typically will encounter. And that's the definition of epsilon delta differential privacy. It's by now a well-established definition. It's very robust. It's a very demanding definition. It's a very strong property that it is requiring. It has some benefits. In particular, it's very insensitive to side information that the attacker might have, so it gives us a lot of protection. It also has some nice composition properties that are useful when looking at several systems put together. So how can we achieve this differential privacy for machine learning? So one idea, first idea, is after we train a model, somehow we try to bound the sensitivity of the parameters of the models to the examples, and then we add noise to the parameters as a function of the sensitivity. So that's great if we can make it work. The problem is that sensitivity is very difficult to quantify, to bound a posteriori. Instead, a better idea is to bound the sensitivity, to control the sensitivity of the parameters to the examples during the training. And here I'm going to assume that the model is trained by stochastic gradient descent. And the basic algorithm is that for each example, we clip the gradient to make sure that the example doesn't have too much influence on the parameters. And then we add noise to the gradient. And this is the approach that is now implemented in the TensorFlow privacy library, which you can get on GitHub and you can use in your machine learning models if you wish. More in detail, we initialize the parameters as usual, and then for some number of epochs, 1 to t, we pick a random subset of the examples, a batch B of the examples. We compute the gradient of the loss for each of the examples separately. We ensure the norms of the gradients are less than some constant c by clipping. Then we add Gaussian noise as a function of c. We average the noisy gradients, and then we update the parameters by a multiple of this average, depending on the learning rate. This basic idea carries over to a lot of different embellishments. You can train with momentum. You can do lots and lots of things as long as it's gradient descent. This basic notion of clipping gradients and adding noise carries over, and it yields differential privacy results. The differential privacy results are theorems. They're things that have formal proofs. The utility is something that we measure experimentally. And by now, there's quite a few papers that include results on utility. And here I picked a table of results from a current ICLR submission. And in this submission, they look at 3 data sets, MNIST, Fashion, and CIFAR-10. And you can see for each of them, they give the baseline without any privacy. That's the line in which epsilon is infinity and delta is 0. And then they train with privacy with several different values for parameters or different techniques. And what you see is that accuracy often drops a little bit. So there's definitely a trade-off between privacy and utility, at least in these examples. But very often it's not too bad. So in MNIST, you lose 0.9%. I have also seen examples in which one actually gains a little bit of utility by training with privacy, but so far those are the minority. Usually one loses a little bit of utility. So there's clearly a little bit more work to do in this direction. There are other techniques for obtaining differential privacy in machine learning, and I'm going to show you one other technique that has somewhat different properties and different trade-offs, and so I think it's interesting as another data point in this big design space. And this is the PATE technique. PATE stands for private aggregation of teacher ensembles. In this technique, one takes a data set, one breaks it up into n disjoint partitions. N is typically a few hundred, maybe 1,000. And one trains separate models that we call teacher models for each of the partitions. And then the teachers are aggregated into one ensemble with a noisy aggregation mechanism. The noisy aggregation is simply counting the number of votes from the models and then taking the majority. Plus, as I will explain in a second, adding some noise. The idea is that if most of the teachers agree on a prediction, agree on a label for an image, for example, then this prediction cannot depend too much on any one example in the data set, because only one of the teachers will have seen that example, because each of the teachers has a different subset of the training data. So that teacher cannot affect the majority. The reason that the majority says something must be because it's a truth that applies across a large part of the data set. This is almost true, but it's not quite true in the case in which there is a very close tie. If the two most popular votes are very close, then maybe one teacher or a small number of teachers can make a difference. So a single example in the training data set might be making a difference. And for that reason, we add a little bit of noise to the counts, noise with a Laplacian distribution in this case. And that means that no one teacher, no one example can make a difference. And that gives a differential privacy guarantee. We're not quite done, though. The use of this aggregated teacher is great for input-output behavior. Any prediction that this teacher makes does not reveal very much about the training data. But at each prediction, there's a little bit of a privacy loss that we rather not bound. And also, internally, this teacher might have memorized some things, even though the predictions don't reveal it. We like to do something that is secure in the white box model, in which an attacker might have access to the internals of the model. And for that reason, we train one more model that we call the student. The student is presented with unlabeled data, and then it turns around and it asks the teachers for labels for the unlabeled data. Once the student is fully trained, we can throw away everything on the left-hand side, and we just use the student for answering queries. And because the student doesn't have any of the internal information of the teachers, it is differentially private in the white box model that we set for ourselves. So there's a lot more going on in this direction. It's getting late, so I'm not going to get into too many details. Some of the more recent work is scaling PATE to tasks with many classes, for example, to a version of Glyph dataset with 150 classes, and getting better privacy guarantees by replacing the Laplacian noise with Gaussian noise, by being selective in answering queries. Sometimes some queries have a very high privacy cost because the teachers have almost a tie, and sometimes those queries are not so useful because maybe the teachers are confused anyway, so sometimes it's better not to answer them. Sometimes it's not worth answering because the student already has a very confident prediction, so maybe it's not worth asking the teachers for help on those. The final set of improvements that I want to mention, I think is very exciting, is that we are beginning to see the use of some state-of-the-art semi-supervised learning techniques in these kinds of privacy approaches. Ian mentioned briefly in his talk semi-supervised learning with a new technique called mixed match that will be presented at New RIPS 2019 in just a few weeks. That technique has been used in combination with PATE, and the mixed match paper has some very nice privacy results that result from using state-of-the-art semi-supervised learning together with PATE. So taking a step back, some things that are interesting about PATE and sometimes nice about PATE, it has decent utility. It's similar in utility to the differentially private stochastic gradient descent. In our experiments so far, it's generally competitive, but we have found that sometimes it's a bit of a stretch to push it to things with many classes. And that's probably the main reason why, in TensorFlow privacy, we have been focusing on differentially private SGD. It provides privacy guarantees, and it provides not only rigorous privacy guarantees, theorems that we can prove about differential privacy, but also a fairly simple story that we can explain to users, regulators, anyone who cares about these majorities and teachers and so on. And we don't need to get into the details of gradient descent and clipping and whatnot, right? It's much more intuitive. PATE is very general. The teachers and the student don't need to be trained by stochastic gradient descent. One can use any other methods, and PATE still applies. And finally, at least in some settings, PATE plays to our strengths. Sometimes we have public unlabeled data, so why not use it? And we have a lot of computers, so we can afford to train many models and then aggregate them into one, and then train one more model as a student. To finish, and then to have a bit of time for questions, I want to put this work on privacy and machine learning in the context of a much longer line of work on privacy. Privacy, of course, was not invented when machine learning came about. There's been work in privacy for probably about 50 years. And there was a very influential paper in the mid-70s by Jerry Saltzer and Mike Schroeder called The Protection of Information in Computer Systems. And in that paper, they talked about privacy mechanisms in a world without machine learning, but many of what they said still makes sense today, or is at least interesting to think about today. And in that paper, they set out some principles for the protection of private information. And I will just discuss a few of them briefly today. I invite you to go look at that paper for the rest. One of their main principles they call psychological acceptability, which means that the privacy protection mechanisms should make sense to users. And the reason for this is that if users and programmers and everyone else don't really understand the privacy protection mechanisms, they're likely to apply them incorrectly, and then errors will follow. And this principle of psychological acceptability is still very important, and in a lot of the work on privacy that appears in the literature today, it's often neglected. We tend to focus on mechanisms that are very complicated and very hard to explain to users and to programmers. Another important principle is the principle of open design. We should not rely on security by obscurity. Instead, we should document our practices, in particular with respect to privacy, and be transparent about them so that they're understood, but also so that if we make mistakes, we can benefit from the community in improving our privacy protection. And the work that we're doing and the fact that we're writing papers about it is, of course, a step in this direction. The principle of fail-safe defaults say that if we ever make a mistake in privacy protection, it should be a mistake on the side of losing utility, not on the side of losing privacy. And of course, we're going in that direction. However, the differential privacy guarantee has some parameters, in particular the delta, that allow for a small probability of error. So the story is a little bit more complicated. and there's more to say on that, and the recent work on Renyi differential privacy gives a clearer picture on this point. Finally, for some kinds of systems, rather than protect private information, it's sometimes enough to detect when the information has leaked out. And I think that's an intriguing possibility, and it's not been explored very much in the world of machine learning. So to finish, I hope I convinced you that there are some really big problems, and they're really important, and that there is a lot more to do. And I'm not going to do it all by myself. In fact, I hope to do almost none of it. So you're all invited to work on this. More technically, there are some very nice and very promising alignments and resonances between modern large-scale machine learning and privacy and security. And these appear sometimes on the technical level. For example, this idea of having multiple teachers and students and so on is a very common theme in machine learning. The idea of adding noise to gradients appears in machine learning for reasons other than privacy. And there's also some coincidence in goals. Generalization and privacy, although they're not exactly the same thing, are going in the same direction. So I'm hoping that these confluences will be useful in allowing us to build systems that are more robust and provide better privacy and security properties, and that enable machine learning to be used in many applications where that robustness is really essential. And with that, I am done, and I thank you for your attention.
Thank you very, very much, Martin, for your talk. We have time for questions. Please, raise your hand. Fede.
So I missed something from the definition. Is that an average over... Is the definition an average over all possible y's, or do you care about individual y's?
Right. So in the definition of differential privacy, the x and the y are universally quantified. So it's a very strong definition. For every x and every y, this should be the case.
Okay.
Yeah.
More questions? Any other question?
Hi.
Hi.
The question is the elephant in the room, maybe, with data mining and that. Who protects the people from Google, Facebook, and other big corporations? What are the actual different legal protection, facing user data and stuff like that?
Mm-hmm.
And it feels a little weird that big companies are going to choose a path that has lower utility and lower performance in order to preserve users' rights or privacy and such. And we have examples in history that show that usually it's profit what drives the company's efforts, right? So I would like to know the opinion. It's not an accusation or anything, but it's interesting to know the opinion of researchers in the field.
Sure. I'm not a lawyer, so I cannot comment on the legal protections, and of course they're different in different jurisdictions, so I'm not sure that I would be able to tell you very much about that. I can, however, talk about some of the rest of the question. Companies, at least some companies, are trying very hard to use data in a way that benefits users. When, for example, we look at data for building a translation system, we do it to the extent that it's going to help users who need to have access to these translations. If the data is not sensitive, we are, of course, not concerned about privacy. If the data is sensitive, privacy is essential, and if you cannot provide an adequate level of privacy, it's impossible to ship a product because you might make a short-term profit, but it would not be a very tenable model, and you would be betraying the user trust, and in the long term, the company would be worse off. So there are cases in which, in order to be able to build the products at all that the users will want, we do need to make a compromise between utility and privacy. The work that Lorena already talked about of using k-anonymity is one example of that, right? And differential privacy goes in the same direction. We're beginning to deploy models with some of these protections. So the question was, what is sensitive and what isn't? In a lot of the work with user data, we make the assumption that the data is sensitive unless we have a proof of the contrary. Yeah.
There's more question there.
I think that related to this is federated learning. Do you apply this?
I didn't have time to cover everything in privacy. Of course, there is going on a lot of work in federated learning. Federated learning, for those of you who don't know it, is a style of learning in which the learning is decentralized. For example, each user's mobile phone might participate in the learning, and only aggregates are collected and distributed back to the other users' mobile phones. So that's an area in which several groups, particularly at Google, are doing a lot of work. And we have been collaborating with some of those people applying differential privacy in the context of federated learning. So they work together. Yeah. All right, it's been a long day. Thank you again.
Thank you very much.